Now,
Welcome, I am Rebecca Schneider. I am a faculty member at the Department of Natural Resources at Cornell University. I do research, teaching, and extension all around the theme of sustainable, ecologically based water resource management. Christy has asked me to give you the presentations about streams, and I've already given you one presentation about the basics processes that help maintain sustainable streams, ecology, hydrology, the geomorphology, and the benefits that humans get by having a healthy stream system. And this is the last section. This is the section that's going to talk about how we need to manage our streams and what some of the major problems are that are facing them, but also the solutions. So that as you now take this information and look at your landscapes around where you live, you can be looking for, oh, I think I can work on that topic. I see that problem might be real. Again, we've covered a lot of material already, but hopefully it gives you a foundation that you need and some tools, places to collect data, techniques to explore that'll help you actually tackle some of these problems. So I'm going to describe these problems or challenges as a series of impacts. I believe I have 6 total impacts, maybe 7. And then I'm going to give you what a solution is to that problem. The first one deals with the headwater systems that we mentioned previously. That is the first and second order streams, the small, narrow ones that make up about 3/4 of the entire stream channel network. And we talked about how important those stream side vegetation is because as canopies that help keep the streams cooler, that provide litter into the streams that fuel the food webs. That's the food that the invertebrates eat. And those stream trees, their roots help prevent erosion. So all these great benefits. However, there's no current legal protection for the headwater streams in the United States. Unless a state has put in its own particular protections, a farmer, a homeowner can clear and mow the lawn right up to the edge of the stream. A farmer can clear all the forest away or the plants and grow corn literally to the edge of the stream. There's no legal protection. It was just a loophole in the 70s and 80s when all of the wetland protection was occurring. These are not legal wetlands because they have facultative species that grow there. The plants that tend to grow in the first and second orders can handle being dry, and they're not obligative wetland species. They're facultative, and that's part of the definition of a legal wetland that gets protection, is that it have the right plant composition. So what's the solution? In New York State, we have an opportunity because the towns control a lot of the environmental protection that happens. And your town can create an ordinance. The town of Ulysses created such an ordinance in 2007. And the ordinance was to require a buffer of where no development can occur and vegetation cannot be cleared, 25 feet wide on each side of the stream, if it's in permanent stream, and 50 feet wide on each side of the stream, if it's a permanent stream. And that ordinance was passed, and it's very powerful. When people come in with a permit to put in a garage or to do some development, the first thing that's asked is, show us the stream if it's going through your property. We use the USGS topographic quadrants, which I described earlier, and a buffer. We put in a buffer and say you cannot develop within that buffer. So you can influence your town local government, and we can get you the website or more information about this as an example of a model ordinance that you could put in place. Impact number 2 are dams. So the dams impact the natural hydrologic regime, and they are barriers to organisms like fish that want to move up and down the stream. There are about 75,000 dams in the United States that are taller than 25 feet. And if you include all dams, there's several million of them. This is a very old figure, but I haven't found a comparable version of it since from 1995. And what it shows for the entire United States are watersheds that have high volumes of water impounded by dams. They're the red. Yellow is moderate volumes of impounded water, and green is low. And what you see is the entire United States, almost 2/3 of the water in watersheds has been impounded by dams. This is a study, and there's many studies now on this phenomenon that dams have impacted the natural hydrologic regime in our rivers. This one shows that 77% of the total water discharge of the 140 largest rivers in North America, Europe, parts of the Soviet Union are moderately affected by fragmentation due to dams. So dams are constructed for various reasons. There are dams constructed for flood control, and they do just what you'd hope they do. They reduce flooding. This is the hydrograph from the Savannah River over the time period before they placed the dam and after they placed the dam. And we had looked at hydrographs in the previous section. And what you see on the vertical axis is the daily mean stream flow or discharge in cubic feet per second. Prior to the construction of the dam, water flow varied from 1,000 up to 300,000 cubic feet per second. Huge flood events would go through relatively frequently. The dam stopped that. It captured those big events, and it also raised the low levels, the base water levels were much higher. This has narrowed the vegetated zone next to the stream. There's not as, because the areas that aren't flooded now, terrestrial species grow there, houses get put there. And because the water levels are higher in the summer always, they don't have as much germination occurring of the species that need to repopulate the forests. A different kind of dam is a hydroelectric dam. And sometimes you have dams that do both of these things, flood control and generate hydroelectricity. This is the typical hydrograph of a hydroelectric dam. Now remember, hydroelectric dams are put in by engineers who are told maximize how much energy we can generate, how much electricity. And when that's the only goal, the best way to do it is to turn off the river, store the water until you want to make electricity, and then turn it on, and then turn it back off. In this hydrograph, the horizontal axis is hours. That means in the course of one day, they turned on the water, the discharge was 5,000 cubic feet per second, then they turned it off. Then later in the day, they turned it back on, and then they turned it off. This is what that looks like. At 3 o'clock on the left photograph is the stream at low flow, and 30 minutes later is the stream at high flow. There are very few organisms that can handle that rapid of a change in the hydrologic regime. They don't have a chance to get away. The velocities are super high. It washes out many organisms. And then when that water level drops, the water is shallow, it gets hot, organisms, fish die, they desiccate, plants don't live there. And so basically you scour all the life forms below the dam for sometimes tens and 20 up to 100 miles further downstream, depending on how big the dam is. So what's the solution? We now recognize we need to operate dams to have environmental flows. That is to protect the natural hydrologic regime as much as possible. You want to, first of all, always maintain some water in the river so it never runs dry. That's like a no-brainer. Never turn the river off, just have lower flows during those low periods. It means less energy is generated. And so that's a compromise. Many states, organizations, agencies, no, we need energy as the top priority. The river runs dry, too bad for the fish. You want to mimic the natural hydrologic regime when highs and lows occur in each year. And when we change the flows, we want to ramp up or down the velocities so wildlife have a chance to respond. There are ways to help fish get past the streams. I'm going to pause just for a second here. Okay, thank you. That was a quick digression there. So they want fish to be able to go up and down the rivers. And so in some places they put bypass ladders, they're called, or stream elevators, that the fish can go up next to the dam and get around it. However, when designing them, we've come to realize a lot of factors have to be taken into account. Many fish cannot jump above about 6 to 8 inches. And so in New York State, that is a photo of a dam from New York State. It's less than a foot high. There are some fish that could not get across up that dam to get to the river beyond it. Certain flow velocities, if they're too fast, some fish can't swim against them. They can't get upstream. They have to be able to detect the entrance to the bypass. It's off to the side. They want to go straight up the stream. How to get attracted to the alternative. The substrate is a key, and the steepness. And then they have to be functional at all different stream discharges, especially in the case of something like mass migrations of salmon. How many fish can go up that bypass at one time? Will handle hundreds of fish. So there's a lot of thought that has to go into designing a successful fish bypass ladder. One that is actually only recently come to our attention is the importance of road crossings. Where a road crosses a stream, they put in a culvert. So for hundreds of years almost, we've had culverts of various kinds. It used to be bridges, but then they became pipes. What happens when the water is concentrated to go through that culvert pipe, it comes out at a high velocity and scours out a hole beneath the pipe. And now there's no way for the fish to get up into the pipe to get through under the bridge. Some good news, and when I teach this class, I have Good News Friday to bring good news that's happening in the world. An organization called the North Atlantic Aquatic Connectivity Collaborative started paying attention to these crossings that were preventing fish from getting into streams to reproduce. And they've done a phenomenal job, including in New York State, where we are now resizing and removing culverts and putting in better culverts. And so here's an example on the left of the screen of a perch culvert in the South Fork of a river that was then replaced with a bigger, wider culvert where water could flow through the stream all the time. And on the right side are salmon passing through a culvert that has been replaced so they can reproduce. All right, impact number 3. Up to now, most of the time we think about fish going upstream, but the reality is a lot of things float downstream. Tiny baby fish, fish eggs, those invertebrates we talked about, float down in what is called passive dispersal or drift. And unfortunately, they are vulnerable to whatever happens to the stream. And in the case of thermoelectric power, incredible quantities of them are sucked into giant propellers and put through a thermoelectric plant where they are used to cool down the water. This is a really giant quantity of water, okay? And since across the United States, this water, let me show you how much water we're talking about. Thermoelectric power, this is a map of thermoelectric power. So these are water used to cool down the thermoelectric power plants. It runs through one time, comes back out the other side of the plant. It's slightly warmer when it comes out, and it's considered non-consumptive use. So it's very rarely considered as a problem. It's just, hey, we're just pulling in the water, we put it right back out the other side of the plant. This is water, the map shows water withdrawals in millions of gallons per day. The darker the blue, we're talking about up to like 10,000 million gallons every day of water pulled from a stream or river, pumped through a plant and pumped back out. In New York State, it was estimated that the steam electric plants use 6 trillion gallons of cooling water every year. And that causes what's called impingement and entrainment. That means these little tiny organisms are sucked in and killed. It's estimated 17 billion fish each year in New York State are killed. These are the larval stages, the egg stages. These are some other data from 2009 for the Great Lakes, with estimates of annual entrainment of larval fish. For Lake Erie, it was 255 million fish per year, 196 million for Lake Michigan, and so on. Those are larval fish. For bigger fish, it was 22 million fish a year. And this doesn't take into account all the little invertebrates that are part of the food webs that are also sucked in and crushed by the propellers or cooked during the heating process and then spit back out. What's the solution? Well, there's a bunch. One, more dams are being removed. I did mention that before. So actually, taking down some of these barriers to movement is one thing. And American Rivers and Trout Unlimited have really done a really great job. And up to about 2,000 dams have been removed in the past several decades. For the entrainment problem, you can actually modify these intake structures. So this is a baby green sturgeon. I don't know if they're still in danger, but they're definitely still threatened. They get up to 5 feet length, but the juveniles are very small, and because they're an endangered species, they had to be concerned about their entrainment. And they tested out different types of structures to put on the end of the pipes that suck the waters in from the rivers. And on the bottom is a graph showing the control where they had the just in open pipe. And on the vertical axis is the percent of the fish that are entrained. 20%, 40% were entrained in the first one, the control. And then they had different structures, A, B, and C. And what they show is that these different structures could reduce the amount of fish that were sucked in and killed. And so you can change the intake structure. The best solution is now not to keep sucking in water all the time. Instead, just use the same water, pull it in, cool things down, let it sit in the pond, cool back down, and pull it back into the plant. And so that's called closed cycle cooling. It's now considered the performance standard as of 2011. It reduces all entrainment of the organisms. It's considered the performance goal for best technology available. And so in some cases it's being required, not all cases, but we have another option that then reduces the impact on our fish and wild populations and young creatures of the streams. All right, impact number 4 is groundwater overdraft. So remember, I mentioned that on average, 50% of the water in our streams is groundwater. The groundwater is what keeps the stream flowing between rain events. It's really critical. Unfortunately, more and more, the world is turning to groundwater as a source of dependable water in the face of climate change with longer, hotter droughts and more people needing water. You put in a pipe underground, you put on a pump, and it's getting very easy to suck water out of the ground. But it takes a while for water to get back to the pipe after you have pumped it out. And what happens is the water in the aquifer, the groundwater, declines. The water table drops, there's less water. And as you can see in this schematic, the water is actually being pumped from the stream. So streams are running dry and getting lower because of our groundwater overdraft. This has an effect on the stream, on the plants that grow next to the stream. And this one particular study, I just really like the way it shows how clearly groundwater overdraft, pumping for communities, caused the disappearance of this entire stream and the forest next to it. This is the Carmen River in California. It has a forest that grows next to the stream, and in this very dry area, it's a critical forest for migrating birds and wildlife to use. It has willow trees and cottonwood trees, which we have a different species, but similar to what we have up in the Northeast. And what happened was they began pumping groundwater, and as you pump it, the water lowers and it gets out of the contact of the root zone. So those trees no longer have access to water and they die. This is a time series of maps showing the reduction in the extent of that forest indicated in black. So at the top is 1956, and in the bottom is the same stream channel in 1980, and you see less and less black, which means less and less forests. And that corresponded to where they were pumping and lowering the water table. To show you how extensive groundwater overdraft is, this is a map of the water table decline. That's a lowering of the top of the water, groundwater, throughout the Ogallala or High Plains Aquifer, which covers about 7 states in the mid-center of the United States. It's been pumped for agriculture to support plant growth, crop growth. And where it's orange, that's a decline of water tables have dropped more than 150 feet. So much of what you're seeing is the water tables are deeper than 50 feet compared to where they should be due to groundwater overpumping. That means the streams are dry, wetlands have disappeared, even the grass communities don't do as well, and it's all used for irrigation. And the solution to all of this is that we really need to manage groundwater. There are some programs in place to monitor how much groundwater is used. They're not very extensive. New York State, parts of the US are getting better and better at that. Globally, there are about 8 different areas globally on the scale of this Ogallala Aquifer where the decline has happened to such a severe extent. Northern Africa, the Mediterranean, Jordan actually will be out of all groundwater in a couple of years, parts of China. And monitoring is the first step. Knowing how much groundwater is there and how quickly it recharges is key. Knowing where the recharge zones are, where's the water come from that keeps the groundwater there, present. And then controlling how many people are allowed to put in pumps and wells and how much they're allowed to take out so it doesn't disappear is the key. Groundwater management is in its infancy. While at the same time that with climate change and more droughts, more and more people are pumping groundwater. So a lot of work needs to be done on groundwater management. Impact number 5 is stream water pollution. So there's all ways that streams get polluted. It can be from sewage, non-point source pollution like sediment washing off the fields. I'm going to just focus on one to give you an example. Road de-icers, salts, are a big problem. They have contributed to high chloride levels in our streams, also in our wells. Sometimes they have to use sand in the wintertime, and highway guys work very hard. I'll tell you about, I'm going to end with a little bit about our ditch program. So they sometimes use sand instead of salt because salt costs more money. And so that sand washes into the streams. The salt will lead to plant die-off near roads and in wetlands, affects some amphibians that live in ponds where the salt washes into the ponds, and it can lead to a salty taste in our water. I talked to some highway guys about why they use so much salt, and what they said is actually people don't tolerate slippery roads like they used to. For example, when I was growing up, people put chains around the wheels of their cars, and you would just drive through the slush slowly with these heavy chains. Now we have tires that help out, but still people don't want any snow on the roads, and so the highway guys are encouraged to put more salt. This is a big problem. So studies are showing that the fresh water in the northeastern United States, both groundwater and surface water, have been increasing in salinity in the past 30 to 40 years to the point where it's undrinkable in some places. That's what these two graphs are. This is the Hudson River Valley. This is the study by Dr. Kashaw and others in New York State, monitoring groundwater salinity and then stream waters and throughout the northeastern United States and showing the salt increasing. There are good solutions and some of them are easy and many are being put in place. So for one thing, don't put the stockpile of salt right next to a stream. This seems like a no-brainer, but in Ithaca, actually, we still have our salt pile right by the canal. We now have rules. Almost all salt piles do have roofs over them to prevent just washing away, and curbs around the outside to capture salt. It takes good housekeeping so that if it spills, it gets picked up. And if the town can afford it, you can use biodegradable alternatives, non-salts like sugar beet or corn derivatives. But the reality is that in New York State, towns have very limited budgets. And so the highway guys really juggle how much money they have for salt to put out, whether they can use sand. And so it's a big issue of the salt causing pollution in our streams. Impact number 6 is pesticides and other toxins. Each one of these topics, by the way, we could spend hours on, but I'm just trying to give you an overview. Pesticides are a huge issue, a really disturbing kind of ticking bomb in my mind. Currently, about 1 billion pounds of pesticides are applied every year in the United States. It's not just farmers. A lot of pesticides are applied by homeowners. They use them for flea control, for weed control, tick control. And so when they look at the amount of pesticides, they did a study, again, USGS did it. They looked all over the country. They measured stream water and groundwater, and they looked for how many different pesticides were present. On the left is a summary of the number of streams that had one or more pesticides in them of all the samples that they took. And for streams, 97% of all streams had at least one pesticide. 61% of groundwater had at least one pesticide. That was in agricultural areas. In urban areas, it was similar. 97% had pesticides. Undeveloped areas were less, but still there's a lot of pesticides moving into our streams, and most have not one, but 3 to 5 or 7 different kinds of pesticides. The studies that look at the effect of pesticides on juvenile fish or amphibians usually look at one pesticide at a time. In the few studies that look at the synergistic effects, they find that you have 2 or 3 pesticides and the impacts are way bigger at very low doses. So we really need to get pesticides under control. A lot can be done with education. to just house owners about how much pesticides they use and how they get rid of the extra. Having hazardous waste collection at the town level is really important. And for farmers, any kind of integrated pest management where they go out and survey the fields regularly. So when a pest starts to take over part of the field, it could be something like a powdery mildew or a Japanese beetle or something. They don't wait until most of the field is affected and then apply tons of pesticides. They deal with it when it's in a really restricted area and therefore don't need to use as much pesticide. So there's whole programs in integrated pest management and use for controlling pesticide applications. Impact number 7 is climate change, because we are now having increased rainfall intensity, torrential downpours, and often they are followed by more droughts. So this was an article in USA Today from May 2013. When rain won't go away, one storm at a time, extreme precipitation. We are currently having about 70% increase in high intensity rain events in the northeastern United States. These are these big torrential downpours, which leads to more flooding in the streams. And so this is a photo of the Endicott Sewage Treatment Plant along the Susquehanna River, taken in June of 2006 when we had a huge flood event. And then 5 years later, in September, the same treatment plant was flooded again. It cost millions of dollars to deal with that first flood event and then to do the repair 5 years again later. So what do we do about this? I mean, obviously the real issue is carbon emissions and global warming due to human effects on the atmosphere. That's the core problem. But how do we adapt? What are the adaptations to deal with this increased flooding that's going to be happening? There are multiple things we can do. For me, getting people out of these high risk zones is a critical first step. Phase retreat, move away. The sewage treatment plants have to be altered in how they're managed or moved to higher ground so that, I mean, it's costing millions of dollars. Why waste the money? But also putting people at risk, moving communities that are in high risk areas up and away from the flooding. And then restoring stream sides where there's no vegetation in those first and second order streams, and therefore they can't capture floodwater for us. So doing stream restoration can also be done. A whole suite of strategies are available, and a lot of attention is being paid to deal with increased flooding. Historically, the flood control structures were the way we dealt with it. We actually tried to get the water out as quickly as possible from the watershed, so we would straighten streams, deepen them. And now we need to look at more organic strategies that actually contribute to the problem. So remember what I said in the previous section about you only have so much water that comes into your watershed. It's a balance. It either moves as runoff or it percolates down and moves as groundwater. And if you can get more water underground, there's less to go into runoff and therefore less it can contribute to flooding. So what we've done to our landscape is actually cause the flooding. We have contributed to the flooding. The landscape prior to European colonization of the northeastern United States was basically all forested. It looked like that in the upper picture. And most of the rainwater and precipitation moved subsurface. There was relatively little runoff. And so groundwater moved slower, it moved slowly into streams. And in contrast, we took that whole landscape and we made it very hardened. We got rid of the trees, we got rid of vegetation, replaced it with parking lots and rooftops. And so most water now moves as runoff and very little goes as groundwater. And what that means is we have caused floods. So pre-development, the hydrograph looked like the black line where it would gradually rise during a rain event and then slowly come back down. And now with the water moving rapidly into the streams as runoff, we actually have faster rise, much higher flood events, okay? And then actually the water drops to zero because we shifted the balance so much that there's no groundwater and the streams run dry. We just have these big flood events alternating with dry periods and dryouts. I feel like this is the bad news and the good news, because the good news is we did that. We can change the landscape and get more water to go underground and less water to race to the streams. dealing with climate change is absolutely critical, but it's going to take a global effort to reduce CO2 emissions. This means every watershed, people who live there can work to reduce the amount of groundwater, the amount of runoff, and get more water to go underground. That brings me to the very last part of all my presentations and the work I've been working on for more than a decade on a very small piece of this puzzle called roadside ditches. Until we actually got working on this, they were the unrecognized factor in stormwater runoff and management. Roadside ditches, we were interested in what role they played in floods and droughts and water pollution. And I'm talking about the depressions that run next to every road that are put there to capture the water running off the road so they don't flood. So it's safe for us. And they also prevent the soil from under the road from freezing and cracking the roads. That's why they're put there. It turns out we started this work and we started mapping all the ditches. Like, let's see where all these ditches are coming from and how do they connect to streams. We monitored what was flowing in the ditches, the total amount of water, what suspended sediment was there, what dissolved chemicals were there. And what we found is that ditches don't just capture water coming off the roads. Instead, ditches are capturing the water coming off the hills that are adjacent to the roads. And they capture about 22 to 25% of all the runoff in every watershed. So this map is the blue line is the watershed divide. The red is the road network. This is a watershed down in Camden, New York. The dark greenish blue is the actual stream channel network. And actually we found there are about 94 places where ditches dump the streams in every watershed on average. And these ditches, so for example, in the left side middle of the plot, you'll see a brown patch. The brown patch is the hill that would normally drain down to the stream, but instead all that runoff is captured by the ditch along the red line and shunted way down further in the stream channel network straight to the stream. So ditches very effectively capture a quarter of all the runoff in each watershed. What that does is it contributes to flooding in the streams. And this is an example of the data we've collected. This is a model. The purple line is what the stream would look like without any ditches. We modeled what the ditches are doing, and the orange line is what is observed. The ditches are causing the stream to flood and discharge by increasing discharge in cubic meters per second by twofold, more than the stream would naturally have just because of the ditch inputs. They are also a source of sediment and associated contaminants, especially when scraped. So the highway guys, we took a survey, on average about half the highway guys in New York State scrape the ditches and do not regrow vegetation. So every time it rains, there's about 120,000 miles of road ditches that are draining, and half of those are scraped, or a third of those are scraped, and the sediment goes straight into our streams and lakes. We are documenting now how significant this effect is on the stream itself. So on the right, you're looking at the stream above where the ditches enter the stream. And below here on the lower right is what the stream looks like after the ditches have entered. And it has widened and scraped out the stream just due to the ditch flow. That's only a distance of about 30 feet. Normally, what you see in the top corner, that's what the whole stream should look like. Instead, it's scoured out during storms and totally changes the ability of the stream to carry water, to have fish, to have invertebrates. So we have an extension program. We are working and have been working for 10 years to work with highway staff about changing their practices. We've gotten the Chesapeake Bay program and Vermont to put in place adopting better management for roadside ditches as part of their programs for their streams and for the Chesapeake Bay. It's moving, it's a major change compared to the 100 years of practices. It takes time, but we're making progress. If you're interested in doing a project, we'd love to have people work with their town highway staff to map the ditches, to look at where ditches are contributing to flooding in streams and erosion and sediment, and just getting the town highway guys to revegetate after they scrape would be a major improvement. That ends my presentation. I hope you've enjoyed it. I hope you feel like you now have some tools to understand how streams function, how important it is that they stay healthy, and what basically all the problems are that are preventing streams from function in a normal, healthy, resilient as ecosystems. I believe I'll get a chance to answer questions from you at a future date. And I wish you all luck with your project. And I really, really appreciate that you all are willing to be master naturalists who go out and help solve these problems. Thank you very much.